Hello, students. Here, this is actually EPR spectroscopy part 2. Hope you won't have sound issue this time because I have tried my level best what I can do for my side. So the remaining part of the basic principle of this electron nuclear hyperfine splitting is that if we take the case of hydrogen atom, then in case of hydrogen atom there is only one electron and there is one proton. So what we perceive that the proton is also magnetically active, so it generates local magnetic field, and the electron it's supposed to is subjected to two magnetic field. One, that is the external magnetic field B, and another is the local magnetic field, that is due to presence of one proton. So had there been no proton, and only one electron would have been there, that is in the case of bare hydrogen, then we would have only one line. But this local magnetic field created due to one proton is splitting the ms value in two further parts, because it can have, the one proton can have either plus half or minus half electronic spin, nuclear spin. So we can find this, we can generate this energy level by this. That is this is the external magnetic field, and this is the local magnetic field generated by the one proton. So this is the case of ms due to electron, that is minus half, and this is plus half. So minus half is resolved in two parts, where minus half is, and this is mi when it is plus half, and this is when it is minus half. Why this is plus half? Because the multiplication of these two terms is negative, so lowest energy possible, that is minus half and plus half. So this is minus, so this will be somewhat of higher energy in comparison to this one. So that's why this energy gradation is found. So what we get, that the selection rule for this EPR transition, when there is electron nuclear hyperfine splitting, is del ms has to be plus minus 1 and del mi has to be 0. So the transition will start from same mi level to same mi level, that is plus half to plus half and minus half to minus half. But the transition is always for ms minus half to minus plus half. So so we get two transitions, and these two transitions are at different position, and the different position mean they are separated by 506 Gauss. The two lines 1:1 intensity ratio, and they are at 506 Gauss, and this is the midpoint of these two lines. This is the midpoint. This is not this figure is actually I couldn't be sincere in making this correct figure, and that's why the distance यहाँ से इतना, इस सिग्नल का जितना डिस्टेंस है उतना ही यहाँ से इसका, and that's why this is 506 Gauss. Now what if so there is two lines in this case, in the case of hydrogen atom. So what if we take the hydrogen ion. In case of hydrogen ion, we have two protons and one electron. So two proton will generate the local magnetic field, and one electron is split in the ESR spectrum like this, minus half and plus half. Now two electron can have these three orientation. So these three orientation is either both the proton will have the same spin, or they have the opposite spin, or they have the same spin. So here in the case, in accordance with the selection rule, that when we make out this, that is minus half and plus 1, because two electrons combined together, their spin combined is equal to 1 plus 1. So this is minus, so this is minus, and this remain unregenerated, unresolved, and this is minus half. So by this we can frame the energy level diagram. And here since in order to do allowance for the plus mi selection rule, the mi, that is the transition, we can have only three transitions. Now these three transitions will have energy gaps are different for these transitions, and so they appear at different magnetic field. And since they appear at different magnetic field, this the middle one, the middle signal is of twice the intensity, because we have the twice the possibility of making the total spin is equal to 0. So by this, now another case, in the case of 2,5 ditersributyl semiquinone, 2,5 ditersributyl semiquinone, we have this two hydrogen atoms, in which on account of delocalization, these two protons exhibit the local magnetic field equally, and so this is the situation in which we dealt with this hydrogen ion, and so this leads to this EPR signal where the ratio is 1:2:1. That is, this middle one is twice the intensity than the other half. So if we take the example of methyl radical, where we have three protons. So 3 protons are there. So 3 protons can orient themselves in this fashion. So in which the plus half and minus half orientation can have threefold degeneration, and that's why we can frame the energy level, and with due allowance for the selection rule that del mi has to be equal to 0. The plus half will go to plus half, plus 3/2 goes to plus 3/2, plus half goes to plus half, and minus half goes to minus half, and minus 3/2 goes to minus 3/2. We get actually 4 lines in due compliance with the intensity ratio, that is the middle two lines. Middle two lines will have threefold intensity in comparison to the end one, last one. Now we can summarize this lecture in this fashion, that when we have the bare electron, we have one signal, and this is the let this be the barycenter. Let this be the barycenter. So when we have one spin nuclei, then one spin nuclei matlab, that is half plus minus half. So it resolves into equally spaced signal at different B0, different field strength. When we have 2 spin half nuclei, then we get the 3 signals, where the 3 signals is actually 1:3:1, 1:2:1, and this is the when 3 spin system is there. So we have the intensity ratio of 1:3:3:1. They are equally spaced. So we can, by this we can frame the Pascal's triangle. We can frame that this is the case. This is the methyl radical. That's the case with the PbSQ, that is para-benzo-semiquinone, in which we have 4 hydrogen atoms, which generates the local magnetic field, and this local magnetic field generates this situation, the methyl radical type situation, where the intensity is given by 1:4:6:4:1, which is very much obvious from the PbSQ EPR spectrum. Now we have the Pascal's triangle, in which that if the nuclei has mi is equal to half, modal half, then this the 2 mi is equal to mi plus 1 is equal to 2. So only 2 orientations are there. So we can form, that is 1, let this be 0, and this is 0. So we have to add two terms together. So 0 and 1 is equal to 1, 1 and 0 is equal to 1. Put another 0 to the left and extreme right side. Add this, that is only 2 terms, that is 1, and this is 2, and this is 1. Put another 0 to left and right. So we get 1, we get 3, we get 3, we get 1. Put another 0 to the left and right. This is 1, this is 4, this is 6, this is 4, and this is 1. So the situation will go on, and this creates the Pascal's triangle. But for non-Pascalian triangle, that is for mi is equal to 1. So 2mi plus 1 is equal to 3. So we will have to add. three terms. So the three terms will be 2 0, that is 1, that is okay, that is 1, so this is wrong, see 1 0 0 0 0, so three terms 1 1 1, so this is 0 and this is 0 0 0 1, this is 2 3 2 1, 1 again 0 0 0 0 1 3 दो एक 3 दिन 6 7 6 3 1. This is the case when the local magnetic field, local magnetically active nuclei has Mi equal to 1. Thank you so much. In the next lecture, we will be discussing the problems over this EPR spectroscopy. Thank you so much.